The topic for today is another classic result in using relaxations for combinatorial algorithms, and that is the problem of Maxcut and the Goemans-Williamson relaxation. So we have as usual, we have a simple graph. We can, it's best to think of it as unweighted, although whatever I'm saying is also valid for weighted graphs. So the problem of Maxcut is find a bipartition. So that's just splitting the sets into S and S complement such that the number of edges going from S to S complement is maximized, which means we're going to maximize the number of edges here. Now note that the minimization problem can be solved in polynomial time. That's the min-cut problem, which is to find a bipartition to minimize the number of edges. Maxcut, on the other hand, is NP-hard. And this is one of Karp's original NP-hard problems. A simple claim that I will leave as an exercise is the Maxcut value is M if and only if G is bipartite. So you can think of Maxcut as a way of measuring how close the graph is to being bipartite. And if it's truly bipartite, the Maxcut value is M. On the other hand, if it is not bipartite, then the Maxcut value will be less than M. And you can think of Maxcut as some kind of measure as to how close the graph is to being bipartite. And so just something worth mentioning is that determining if G has a Maxcut of M is in polynomial time. Indeed, there is a linear time algorithm to determine if a graph has a Maxcut of M, just determine if it's bipartite, and then the bipartition actually gives you the Maxcut value. Okay? And so we know it's NP-hard, and so a natural question is, what about approximation algorithms? And so here's another sort of simple but fairly classic result known. Take a random cut. And this is really like a uniform random cut. This yields a half approximation, which means we can cut at least half the edges of a Maxcut, because this is a maximization problem. And unlike many of the problems we've seen in a minimization, the approximation factor is more than 1. In a maximization problem, the approximation factor will be less than 1. So what do I mean by a random cut? I'll just say that each vertex is placed in S independently with probability exactly half. And so that's what a random cut is. So I can alternately say that as this xu, which is the indicator. So this is the indicator, is 1 with probability half and 0 with probability half. So it's just uniform random coin toss. And the claim is that the expected value of the number of edges cut from S to S complement, this expected value is at least m over 2. That a random cut will actually cut half the edges. And so this gives a half approximation because the max cut value is at most m. And the proof is simple. It's basically just linearity of expectation. Okay, so for edge E, let XE be the indicator for the edge E being cut. So what this means is, here's our graph. We set some of these to be 0, some of these to be 1s. Then we put all the 1s on one side and all the 0s on the other side. And we look at how many edges are cut. Now let's look at a specific edge. We can create an indicator random variable for the edge E being cut. What is the probability that this edge is cut? What is the probability that this edge is cut by the random cut? Any guesses? What is the probability that a random edge is cut? Or sorry, not in a random edge. What is the probability that a specific edge is cut? Right, so you take an edge, and for every endpoint you flip an independent, unbiased coin. And if the coins come out to be different, they're on different sides, and the edge is cut. If the coins come out to be the same, they're on the same side, and the edge is not cut. So the probability is exactly a half. So probability is exactly a half, and so the expected number of edges cut we can write as the expectation, the sum over all edges of XE. And I should say this is also the same thing as the expectation of XE. Right? The probability that it is 1 is the expectation of XE. So we sum over all edges of the expectation of XE, and this gives you exactly m over 2. So not only is it greater than or equal to, it's exactly m over 2. So what this proves is that the expected value of a random cut is at most m over 2. The max cut value is clearly at most m. And hence, a random cut gives a half approximation. Any questions about the half approximation? Any questions? Fairly straightforward calculation. But there are a few interesting points to note. It's a nice combinatorial statement. It's a nice combinatorial theorem because it asserts that every graph has a max cut value of at least m over 2. It says that there's always a cut where you can, where you cut at least half the edges. And this is a very simple half approximation algorithm. This is a randomized algorithm. It can be made deterministic, and I'll probably give some exercises about that. But we have this very simple half approximation algorithm. It is surprisingly hard. It's surprisingly hard to beat a half. And what was shown by, this is by Polyak and Tuza in 94, and then shown by De La Vega and Mathieu in 2007, that many LP relaxations of Maxcut have an integrality gap of a half. So most LP relaxations actually have an integrality gap of half, and it is not clear how one can beat the half approximation because many tools were tried and they did not work until the seminal result of Goemans and Williamson in 95 that gave a 0.878 approximation for Maxcut, and they introduced two very novel ideas. They used something called an SDP relaxation and a technique for rounding called random hyperplane rounding. And the point of today's lecture is to demonstrate, is to show these techniques to you. I'll explain what an SDP relaxation is. SDP stands for semi-definite program, and I'll explain what that is. And then we'll do the randomized hyperplane rounding for Maxcut. Analogous to what we did for conductance, where we used a quadratic program, an integer quadratic program, to represent sort of the, to compute, or we represented the optimum through an integer quadratic program. We will formulate an integer quadratic program for Maxcut. So here's an integer quadratic program. Surprisingly simple program. It just says maximize. So for all edges UV, we want to cut them. So we're going to basically set for all vertices V, xv is either going to be -1 or +1. So think of it as here's -1, here's +1. Every vertex has to be placed either here or here. And if they're placed on different sides, the edge is cut. And if they're placed on the same side, the edge is not cut. And so what you get is simply xu minus xv square. We divide by 4 because when xu and xv are different, then their value is 2, right? Because -1 is, the absolute value of that is 2. And so 2 squared gives 4. So for every edge where the vertices are on different sides, you get a contribution of 1. And this is the integer quadratic program. Any questions about this? Okay. And so how to relax this? So a natural thought that you might have is we can set xv just to be in the continuous range -1, 1. And analyzing this is challenging, but Trevisan in 07 related this relaxation to actually the maximum eigenvalue of the Laplacian, and there's a fairly non-trivial rounding. It's a fairly complex rounding procedure, and you can get something like a 0.71 approximation using it. But as I said, Goemans-Williamson in 95 gave something, using semi-definite program, which has not been beaten. And for good reason, we don't think that it is possible to beat that. But just to say that relaxation, the one that we did for conductance, it does have relations to spectral graph theory. But the idea that Goemans and Williamson had was a rather extremely novel idea. What they said was, what if instead of thinking of xv's as scalars, we actually thought of xv's as vectors? So consider xv to actually be a vector in d-dimensional space. Think of it as a vector. So instead of putting points, so in this case, you could think of the discrete solution chooses one of two different vectors. Right? xv is either this vector or this vector, so it's just one dimensional. And one way to relax this would be to allow the vectors to be in higher dimensional space. And so what they do is allow xv to be vectors, unit norm vectors. And so the relaxation is to again maximize over all edges, except now put the 2 norms squared, again divided by 4. And we set this norm to be 1. Okay, any questions about what this is? So this is the Goemans-Williamson relaxation. Now, firstly, there are two questions here. Probably the first most important question is, how can we solve something like this in polynomial time? And secondly, if we have a solution, then how do we actually round it to get an integral solution? So this is, I'm going to get into the first part in showing you how such a mathematical program can actually be solved in polynomial time. But before I get into that, any questions about this? Is this clear? Right? So it's going to be convenient for me just to open up this expression. And if I open up this expression, I get the summation over all u, v, and e of xu square plus xv square minus 2 xu dot xv divided by 4. And so this is just 1, and this is just 1 because we assume that the norms are 1. And so if I write out what it is, what we want to do is we want to maximize the summation. So let me ignore it. The expression becomes 2 minus 2 xu dot xv divided by 4, or moving things around, I get m over 2 minus half times the summation over all uv of xu dot xv. And this is now a dot product between vectors, right? So we want to maximizing this under this constraint that all the norms are 1. And so we can also treat this as minimizing the sum of dot products. Right? So all of this is again equivalent now to simply this program, minimize for all edges UV, minimize the dot product subject to the norm being 2 norm, sorry. Right, so ends up being a fairly simple program to write. Now, why can we solve such a problem in polynomial time? So first, let me tell you what is this problem. This is called a semi-definite program in SDP. So what are the characteristics of an SDP? So let yuv be equal to xu dot xv. If I were to write this, then I could write this as simply the sum, the minimum over all edges uv of yuv, and then for all v, yvv is equal to 1. So essentially an SDP is a linear program with variables that are dot products of vectors. Somewhat informally stated, and I'll state this more formally shortly. But the point is, you have a linear program now. These are all linear constraints. Right? All of these are linear constraints. There's a linear objective. But the variables are actually dot products of vectors. And SDPs can be solved in polynomial time, which is quite surprising. And the way to do it is actually using the ellipsoid method. So we can use the ellipsoid algorithm to actually solve SDPs in polynomial time. And so technically I should say maybe weekly polynomial time using the ellipsoid method. And I will describe how we're going to do that. So remember, there are really it's useful to think of two kinds of variables. There's the x variables, where the x's are vectors. So I'm just going to put vectors on top of those so that we can see those explicitly. So let's think of the variables as a matrix capital X, where these are going from x1 to xn. So I'm putting these vectors as column vectors of a matrix. The dimension d, we can think of the dimension d as just n. And that's because we only care about dot products, so we can think of all of this being in n-dimensional space. So these are our variables. This is what we are trying to find. Now, the matrix Y is X transpose X. And this is called the Gram matrix or the Gramian. Gramian or the Gram matrix. What we have are linear constraints and objective over the entries of the matrix Y. Right? So the Gramian, so what we have is we have our variables Our original variables are in this matrix. We take the gram matrix. So what is the gram matrix? This is the matrix of dot products. This is the matrix of dot products. Right? Because YUV is exactly XU dot XV. Okay? YUV is exactly XU dot XV. So we have linear constraints over the entries of Y. Now, Y is a very special matrix. Note that if you just said that if you didn't have any constraint, then this is just an LP. Right? If you simply wrote this over here, that's just an LP. But you are constraining these variables to be related to each other through being dot products of some set of vectors. So Y has a very special property, and this is something that we also saw while doing the Cheeger inequality. So I'm going to define something here. I'll say a matrix M is called positive semi-definite. This is called PSD. It's called matrix is positive semi-definite if M is symmetric and for all vectors X transpose MX, this is the Rayleigh quotient, is greater than 0, right? So this is the Rayleigh quotient. So a matrix is positive semi-definite if, we'll assume that all the matrices we look at are symmetric. If for all vectors X transpose MX is greater than 0, gram matrices are PSD. And we can see that quite easily. So let's take X transpose, let's use Y. Right, so X transpose Y X. Maybe I'll just call this Z instead, just so that we don't interfere with X. So Z transpose Y Z. Now this is equal to, right? So these are vectors. Z transpose X transpose X Z. Now I can write this as X Z transpose times X Z. So this is just a vector dot product with itself, which is a norm, and this is greater than or equal to 0. So gram matrices are positive semi-definite. Gram matrices are positive semi-definite. And so going back to what is an SDP? What is an SDP? So let's go back and define an SDP is really linear program over the entries of a PSD matrix. That's what an SDP is. So you have a linear program, except you constrain all of the variables to be entries of a PSD matrix, a positive semi-definite matrix. That is an SDP. It's still not obvious how to solve this in polynomial time, which I will get to. But this is the definition of an SDP. And the Goemans-Williamson relaxation of Maxcut is an SDP, because what we have are linear constraints over entries of a positive semi-definite matrix. In this case, it's a gram matrix. Any questions about that? Any questions about this? So again, in the linear program over here, the variables of the SDP you should think of are y, although we said y is equal to x transpose x, and we care about x, not y. We care about x, not y. So if you solve the SDP, you will get a matrix y. You will get the matrix of dot products. So it's like when you solve a linear program, you get a vector. You get all the values x, all the variables. In this case, the variables are dot products. So what you get are all the dot products when you solve the SDP. What you want are the vectors. So I'm going to show you how to get the vectors, which is independent of how you're going to solve the SDP. I feel I'm going a little fast here, so I will pause and take any questions that you have. So please ask me any questions about PSD matrices or what is going on over here. Does everything make sense? Okay, then let me proceed. So linear program over entries of a PSD matrix. So let me just sort of draw a picture here so that we understand. So the Maxcut relaxation, which I'll just write over here, it was just the min sum over uv in E y uv for all v y vv is equal to 1 and y is equal to x transpose x. This is the Maxcut relaxation. So the SDP solver basically takes this and returns y. It returns a PSD matrix. So it says the Maxcut relaxation would simply be, okay, we're just going to sort of scratch that out and we'll just say y is a PSD matrix. So it returns y. Now from y to get x, there is something called a Cholesky factorization, which given y computes a factorization of y being equal to x transpose x. So any PSD matrix can actually be factored as a Gram matrix. So there is this relationship between PSD matrices and Gram matrices. Essentially, there is a correspondence between them. So a Cholesky factorization will factor a PSD matrix in this form. And so this would be your pipeline of the algorithm. You start with the relaxation, you give it to an SDP solver, it returns a PSD matrix. The PSD matrix is then factorized to get the vectors. Now, I don't want to get too much into Cholesky factorizations and things about that, but I want to give you some intuition as to why this is even doable. So I'm going to state an important lemma here. And then from this lemma, I'll show you how to do a Cholesky factorization. So I'm just going to state an equivalence here. I'll say matrix M is PSD is equivalent to, remember, M is symmetric, so all the eigenvalues are real, is equivalent to saying all eigenvalues of M are non-negative. I mean, that's exactly, these are equivalent. So PSD, remember, the way we said PSD is that Z transpose M, Z is greater than or equal to 0 for all vectors Z. This is equivalent to saying that all the eigenvalues of M are non-negative, and this is exactly related to the Rayleigh quotients, which we discussed during in the lecture on the Cheeger inequality. Okay, so how do you get a Cholesky factorization? There are more efficient methods than what I'm going to tell you, but what I'm going to tell you hopefully will give you some intuition behind it. So we start with Y. Y is PSD. We can compute the Eigen decomposition. Right? So what that means is you have eigenvectors lambda 1, let's say lambda 1, lambda 2 up to lambda n, and the eigenvectors u1, u2 to un. Right? So you can compute this in polynomial time. You could do this, you can do something like Gram-Schmidt or whatever. You can compute one eigenvalue, not maybe Gram-Schmidt is the, you can compute one eigenvector, and then you look in the orthogonal space and so on and so forth, and these are all orthogonal. Okay, so if you've seen SVD, then given the Eigen decomposition, you can write Y is equal to V transpose sigma V, where V is essentially the orthonormal basis. This is the orthonormal basis given by the eigenvectors, and sigma is just the diagonal matrix of eigenvalues. So if you compute the Eigen decomposition, you can factorize Y in this form. Now the lambda i's are non-negative, so you can actually write Y as V transpose square root of sigma V transpose, and what you have is you have your Gramian representation here, V transpose sigma V. So this now becomes your X. This is just to show you that a factorization is possible. So if you compute all the eigenvectors and the eigenvalues, then you can compute this decomposition. This is an overkill. It turns out you can do things more efficiently than computing everything from scratch, or rather computing all the eigenvectors, and that's what a Cholesky factorization does. And this is a very common method used in numerical methods and used in a lot of scientific programming and solving linear systems. Appears a lot in machine learning methods where you compute a Cholesky factorization of a PSD matrix. Now from our standpoint, we will ignore the actual computations and we'll just say, okay, given Y, you can compute a factorization, and this is factorization in, it's in polynomial time. I think technically it's something like you can do it in O of n cubed time. Okay. So the part that I'd like to focus on is how do we actually solve an SDP? How do we solve an SDP? So how do we solve an SDP? So remember now again, the SDP is now this formulation, right? We have linear constraints on the entries of a positive semi-definite matrix, and we want to solve this. So think of Y as a vector in R to the n squared. So instead of, it's a matrix, but you can also think of it as a really long vector just by putting the rows one after each other or the columns one after another. So think of Y as a vector. So what I'm going to do is I'm going to create a convex program. Think of y as a vector. And so if you want to think of it as space, consider this the region of PSD matrices. Right, so any PSD matrix, you can think of it as a vector in n square, and you could think of in space, you have all the PSD matrices. So first claim is that this region is convex. Okay, so let me give you a proof. Consider PSD matrices M1 and M2 and a convex combination. Maybe instead of lambda, let me use something else. Let's say mu times M1 plus 1 minus mu M2 for mu being between 0 and 1. Right? So to prove that it's convex, I just need to show that all convex combinations lie in the set. So I'm going to show you that this matrix here, which you can also think of as a vector, but I'm going to sort of switch between this vector in n square and a matrix, this matrix. I'm going to show that this is PSD. So I can just say for any z transpose mu m1 plus 1 minus mu m2 times z is equal to mu times z transpose m1 z plus 1 minus mu z transpose m2 z. Now this quantity and this quantity, these are both greater than 0 because M1 and M2 are PSD, and hence this is also greater than 0, and so this matrix is also PSD. So a convex combination of PSD matrices is PSD. So if you think of y as a vector, these PSD matrices as vectors in this space, our SDP is a linear program over the entries of a PSD matrix. So the SDP defines a convex region, right? Because the PSD matrices are convex, and then on top of this you have some linear inequalities, right? So essentially you could think of this darkly shaded region. This is your body, right? So note that it's not an LP because some of these boundaries, they aren't facets of a linear form, but they're all basically the region of PSD matrices which is convex. So you have some convex region, and in this convex region you put linear constraints, you end up with a convex body, and hence the SDP defines a convex region. So the SDP defines this convex region. To run ellipsoid, we need a separation oracle. So as long as we have a separation oracle, then we can run the ellipsoid algorithm. So just recall, what is a separation oracle? Just reminding you, a separation oracle is given any y, determine, so it defines a conic region, which I'll refer to as script C. Determine if y is in C, or I'll put a separating hyperplane. Okay? So the linear part of the SDP is easy to handle. Meaning, we can just say that if y violates any linear constraint, then we have a separating hyperplane. But what if y is not positive semi-definite? So what if it's not a PSD matrix? How do we get a separating hyperplane? So remember, I said if a matrix is not positive semi-definite, then by definition there exists a Z such that Z transpose MZ is less than 0. Okay? So if Y is not PSD, there exists a vector Z such that Z transpose YZ is strictly less than 0. Okay, now remember that I was thinking of Y as a vector. So it's useful to see what Z transpose YZ is. So I'm going to draw this as a picture. So this is Y. This is Z transpose. This is Z. Right? So this thing is essentially the sum over all ij of Zi Zj times Yij. And that's exactly what the Rayleigh quotient is. But if you think of this term together and this term together, it looks like a dot product. So it's the same thing as if you consider this vector y, where all the entries are Yij, and if you consider this long vector where the ij entry over here is Zi Zj, then it is the dot product of these two vectors. Another way of putting this is, what is this? This is the outer product ZZ transpose dot product with Y. So if we want to think of I'll call it a bullet product. So you think of Y as a matrix, ZZ transpose is a matrix. So this is ZZ transpose, this is Y. The bullet product is basically like treating them like vectors and taking an entry-wise dot, taking a dot product as if they were vectors. So if Y is not PSD, then there exists this vector Z such that Z transpose YZ is less than 0. That's the same thing as saying that all of this is equivalent to saying that if Y is not PSD, there exists a vector Z such that the outer product ZZ transpose dot Y is less than 0. This defines the separating hyperplane. right? So this defines the separating hyperplane. Any questions about this? So I'll pause here and take any questions that you have about this, because this is a very important point on how the separation oracle is built. So this is the set of all PSD matrices, right, in that space that I drew. And Y is over here. Now, if you choose any PSD matrix M, note that, so Y is not PSD, then there exists this Z. So think of ZZ transpose is defining a direction in this space such that all PSD matrices lie on the positive side and Y lies on the negative side. So for all M which are PSD, ZZ transpose bullet product with M is greater than or equal to 0. But for Y, it's less than 0. So if I look at ZZ transpose, it's kind of like defining, so think of ZZ transpose as like this direction here. Because any vector defines a normal. Y is on the negative side, but all the PSD matrices are on the positive side, and that's a separating hyperplane.
Yeah, I think it makes sense now.
Yeah, so hopefully this picture makes, so the thing is that the certificate of being not PSD actually ends up giving you a separating hyperplane. And that's why you can use the ellipsoid algorithm. It's quite non-trivial. I mean, the fact that this convex body actually has a separating hyperplane comes from the fact that you can rewrite the Rayleigh quotient as a dot product. I mean, okay, in some sense that's because of the linearity of the Rayleigh quotient, but does that make sense? Hopefully that clarifies some of this. Of course, the question is, how do you find this Z now? So any thoughts on if it's not PSD, how do you find a Z? So what do we know if it's not PSD? What do we know about the eigenvalues?
There should exist a negative.
Exactly. Good. So there should exist a negative eigenvalue. Can you now find some vector so that Z transpose YZ is less than 0?
Oh, it should then just be the corresponding eigenvector.
Exactly. The corresponding eigenvector will give it to you. Exactly. Right? So what we could say is, now let me describe the separation oracle for SDPs. Right, so first check that Y is symmetric. Symmetric and satisfies the linear constraints. If not, we find a separating hyperplane. So this is the easy part. Otherwise, what we do is compute the smallest eigenvalue of Y and corresponding eigenvector Z. If the eigenvalue is is greater than 0, then y is PSD, and we certify that y is feasible. If not, then Z transpose y Z is equal to the eigenvalue which is less than 0. And so the hyperplane defined by ZZ transpose, or technically you can say the hyperplane normal to ZZ transpose, is a separating hyperplane. And so this gives a polynomial time separation oracle. All of these steps can be done in polynomial time. All steps doable in polynomial time. So SDPs can be solved. SDPs can be solved using the ellipsoid algorithm. Okay, so what this says is we can solve the SDPs in polynomial time. So let's sort of pop back all the way. So even if you haven't followed any of this, the whole point of all of this was simply to argue that this program, which is to maximize the sum, because we could look at this program which is the same as the original program. The original program can be solved in polynomial time, which is the maximizing xu minus xv squared, the distance between them squared, subject to this constraint. So I'm just going to write this down once more and say, okay, so we're maximizing the sum over all uv and e xu minus xv squared, such subject to for all v xv2 norm is 1. This can be solved in polynomial time. So even if you were lost so far, you can come back and we can follow the rest of the argument without any reference to the previous argument. So let's just say you solve this. And so your solution is now some set of vectors. How do you round these vectors? So the rounding, and this is an important technique that was introduced here, was simply pick a uniform random hyperplane to define the bipartition. So what that means is you just choose a random hyperplane. Sorry, this is messed up. So here's my random hyperplane. This is random. And so everything on one side will say this is S and this is S complement. This is how we're going to round it. We're just going to choose a random plane to cut. Just as a comment, how do you choose a random plane? Well, you just set W. So you can assume that this sits in n-dimensional space such that each Wi is sampled from a Gaussian. So this is a Gaussian distribution. Gaussian with a mean 0 and variance 1. And so you can generate this random vector, and this vector W, this vector is spherically symmetric. I don't want to get into the details of why that's the case. You can just validate this. You can just check this by by computing the PDF of of this distribution. So this is spherically symmetric, which means that it essentially is a random vector. It gives you a random direction. And then what we simply say is, remember, we have these vectors over here. And we'll say that...
hi, Sesh.
Yes.
May I ask, how do you round a vector? I lost it here.
So I'm going to describe that right now, actually. I'll describe it formally, and then if it's still confusing, ask me. So I'll say that V is in S if and only if xv dot w is greater than or equal to 0. This is the rounding. I need to get a set, right? That's how I get my set. So I just pick a random vector, and if the dot product is positive, then I say it's in the set, otherwise it's outside the set. That's the rounding. Does that answer your question?
Yes, but there are a lot of random vectors you can choose. So how do we choose that vector?
Just pick, you pick one uniformly at random. You just pick one uniformly at random. You just pick one according to this process. So you choose a vector by simply for every coordinate sample a random Gaussian. That gives you a vector, and just use that vector.
Yeah, I got it. So there is a Gaussian distribution.
Yeah, so you use an independent Gaussian. I mean, this really isn't that important whether you use a Gaussian. You can even just use plus minus ones. And it turns out like...
the difference?
Well, I mean, okay, so Gaussians are going to be better behaved. The math is going to be a lot easier.
Okay, I'll later on do the calculation there. I can't see the calculation right now.
Yeah, it's okay. So I mean, it's spherically symmetric because essentially, I can just write this out like really quickly here. So the probability distribution, right? So what you get is that, I mean, ignoring constants, right? The probability distribution is something like e to the minus wi squared for each Gaussian. And you're doing it independently, so you get a product over all I. If you write this out, you get e to the minus summation of wi squared. And this is exactly the 2 norm.
Yep.
So this is spherically symmetric because it only depends on the norm. It doesn't depend on the direction.
I see.
Right? So this gives you something that is spherically symmetric, meaning that on the sphere it's sort of uniformly distributed. So this is why you use Gaussians, because then the numerator basically you get a sum in the exponent, which is the norm squared. So this is the rounding procedure, right? So you basically pick a random vector w, and you say that if it's positive, then it's in S, and otherwise it's not. Now, how do we do the analysis? And this is really neat because it ends up being some very simple trigonometry, but it's quite remarkable. So we'll say, what is the probability that UV is cut? So it turns out we can draw this out. So consider the plane containing the vectors xu and xv. Okay, so I'm just going to draw these out. These are 2 vectors here. I'm going to make a comment here. This is, it's an exercise that it doesn't require work, but you have to think about it a little bit. That the exercise is the SDP solution ensures that for all uv in E, the dot product xv is going to be strictly less than 0 or less than or equal to 0. You can actually argue that all the vectors are going to be obtuse angles. Right? So they're basically, if the dot product is less than 0, the angle is obtuse between all pairs of vectors. Okay? So we can, all pairs of vectors corresponding to edges form obtuse angles. This isn't particularly important for the analysis, but it's useful to sort of keep in mind. Okay, so here's our plane that contains it. We are going to choose a random direction. We're going to choose a random direction, and we want to see what is the probability that one is on one side and the other is on the other side. That u, so let's just say this is xu and this is xv. So I'm going to draw out a few directions here. So first, this is just extending it here. And I'm going to now draw this so that this is a 90-degree angle. Just drawing this direction out. And then I'm going to draw this direction here so that this is a 90-degree angle. Okay, I'm just drawing these directions out. Okay, now let me look at W. Consider W projected on this plane. Suppose W lies here. Question: is UV going to be cut or not? Is the edge UV going to be cut or not?
It should be a cut, right?
Yes.
So
Yeah, go on, because?
one of them is less than 90 degree, the other is greater than 90 degree.
Exactly. So it's going to be cut over here. So here it's going to be cut. By the same logic, it's going to be cut over here as well. Right? Because if W lies in this region, then the dot product with V is positive, but with U is negative. So it's cut here and it's cut here, but is not cut here. Okay, so I'm just going to draw this picture again with a little bit of cleanliness here. Let me refer to this angle as theta UV. As theta UV. And of course, you can have a symmetric picture in the other side, but let me just assume that W lies in this positive region, in this region. What is the cut angle compared to theta UV? Right? I'm just drawing this with dotted lines here. Compare this cut angle, like this angle plus this angle compared to theta UV. How much is it? Can you see? More or less. So if W lies anywhere, so let's just say that W lies in this region. You're picking a random vector, and this random vector is going to lie somewhere in this region. Just the upper region, because the lower is going to be symmetric. If it lies in here, UV is cut. If it lies in here, UV is cut. If it lies in here, it's not going to be cut. So the good event for us is that it gets cut. Can you compare that to the angle between XU and XV? Anyone wants to hazard a guess?
Are they the same?
They are the same, exactly, because this part here is equal to this part here, right? And everything else is contained in here. So the cut portion is equal to theta UV. So the probability that UV is cut, we chose a random angle. So you chose something at random in here is exactly theta UV divided by pi. We're measuring in radians. That's the probability that UV is cut, which makes sense that if UV is actually pi, the probability is 1, right? If because they're going in opposite directions, it's 1. If theta UV is pi over 2, then it's exactly a half. And we remember, we assume that all pairs of vectors correspond to angles forming obtuse edges, or I should say not obtuse, but non-acute, really non-acute. Okay. On the other hand, so let's compare this with the objective value. Remember, this is the usual thing we do in randomized rounding, right? We look at an edge, we say, what is the probability it's cut compared to what is there in the objective? So technically, this is divided by 4. Okay, so the objective for UV is xu minus xv squared divided by 4. And, using our basic trigonometric facts, this is the cosine of theta UV divided by 4. So I get 1 minus the cosine of theta UV divided by 2. So this is the probability that it's cut. And this is what you get from the objective. I will just rewrite this as follows. So the probability that UV is cut is equal to theta UV divided by pi times 2 divided by 1 minus cos theta UV times xu minus xv squared divided by 4, right? This is what I get from the objective. I'm just rewriting this. So I get this bizarre function here. 2 divided by pi times theta UV divided by 1 minus the cosine of theta UV times this is like the cost of UV, but not really the cost here, it's the gain, because so this is like the objective for UV. So I want to show that the probability is high. Remember, I just want to say when theta UV is equal to pi radians, theta UV is pi radians, this quantity is 1. When theta is equal to pi over 2 radians, the quantity is also 1. You can verify that. When you put pi over 2, you'll get 1, because the pi over 2 cancels with the 2 over pi, and cosine of pi over 2 is 0, so you'll get 1. How am I going to sort of upper bound this quantity? I'm just going to do a very crude bound. I'm just going to say, well, this is at most the min over all possible values of theta going from the min of theta going from pi over 2 to pi, because I know that the angle lies pi over 2 to pi, times this of this function times the objective for UV. And overall, let me refer to this as alpha Goemans-Williamson. This is just some constant. What we know is that the expected cut value, because I just sum this over all edges, is at most alpha GW times the SDP opt. Right? And so this is going to be my approximation factor, approximation ratio. So what is this quantity here? This is some strange looking quantity. So what I did is I just wrote a Python script to just generate all of the values, and I'm plotting it and showing it to you. And so let me just show you what this is. Does everyone see the screen here?
No.
No. No, nobody see anything? Hang on. So I will just share a screen here. Do you see it now? No?
Not yet.
Not yet. Wow, okay. This is surprising that I'm not able to get this to work. This is annoying.
But earlier you say you're starting to share your screen.
Was it?
Like earlier, it seems like you're still still trying to process. You said you have started screen sharing.
Okay, let's see if this works. Otherwise, I'm going to have to draw it by hand probably. Okay, Zoom seems to have frozen on me, which is annoying. You can at least see my screen, right? You can see what I have over here.
You mean your
My document camera, like what I'm writing.
Yeah. Yeah.
So I'll just say that this turns out to be 0.8785. It's some strange number. If you plot, which hopefully I was hoping to show you, is if you plot it at pi over 2 and pi, at both of these it's actually 1. And it's this convex curve whose min is at 0.878. And this is the Goemans-Williamson ratio. So this rather strange quantity, if you minimize it over all delta, then you get it. Has anything happened? All right, I'm just going to stop the share. It's a bit of a bummer. But I actually had the value plotted, but it doesn't want to show that. Okay, so maybe you can see the screen now at least. Okay. Okay, anyway, so the thing is, if you compute this value, then it turns...
I don't think I can see your screen.
Sorry?
I don't think I can see your screen.
You don't think you can see my screen? Okay, that Zoom seems to have conked out over here.
No, it's fine.
It's working now. Okay. So yeah, unfortunately, I wasn't able to show you the plot, but you can essentially compute this numerically and you get this funny value of 0.8785. And so that gives the Goemans-Williamson approximation. So it's a significantly big improvement from a 0.5 approximation, 0.8785. Any questions about this? Okay, just a couple of maybe parting comments here. Remarkably, this is believed to be the best possible in polynomial time, best possible approximation ratio in polynomial time, which is quite surprising. It's this very strange function over here. Yet this minimum of this strange function actually ends up being what is believed to be, and there is some reason for this. This is related to something called the unique Gomes conjecture. This is related to the unique games conjecture. And there is a matching integrality gap. So I'll show you a simple integrality gap, which comes pretty darn close of something like 0.8844, so on and so forth. And this is a simple example. So let G be the 5 cycle, right? So it's just this graph here. What is the max cut value of the 5 cycle? Any guesses? How many edges can you cut?
Two.
You can cut 2. You can do better than 2. You have to move things around. Put 3 vertices on one side and 2 vertices on the other. Except, don't do them in order. Do it this way. And so this becomes S and S complement. And so the max cut value is 4. You can cut 4 edges. You miss the 1 edge. Obviously, you can't cut 5 because it's not bipartite. The SDP solution. The SDP can do this. What it can do is actually... Okay, so I'm just going to draw the pentagon here. It's going to put the vectors in this form, but the edges are going to go this way. So it's going to actually embed as a star. Right? So these are the edges. So it's going to orient the graph as a star and use these. And so the theta UV is essentially this angle here. And so theta UV you can show as something like is 4 pi by 5. And the SDP opt, because it gets this for all edges, is essentially going to be something like for all the edges it gets 1 minus the cosine 4 pi by 5 divided by 2. So the SDP opt you'll get is something like 4.522, so on and so forth. So the integrality gap is the ratio of these quantities. And so the integrality gap is at most, it could even be lower than this. So what you get is 4 divided by 4.522, and you get something like 0.8844. So you get a simple integrality gap of 0.8844, and you get a rounding scheme of 0.878. So actually that example is pretty close to the 0.878, but with a far more complicated construction, you can actually get the integrality gap exactly of this. You can construct a bunch of vectors whose angles are precisely going to be the min of this, and you construct a graph so that, you know, the probability of getting each edge is exactly this quantity. And so overall, like what this does is this gives a fairly well-rounded picture of Maxcut and the SDP relaxation. So again, the important point is that Maxcut can be relaxed as a semi-definite program, which is a linear program over dot products. It's a linear program over dot products. One can solve that using ellipsoid. Once you get those vectors, you can pick a uniform random hyperplane to sort of get a bipartition, and then you have to do, you know, some amount of trigonometric calculations here. But what you can show is the probability that the edge UV is cut is at least 0.8785, you know, there's some constant, times the objective value. And this is the Goemans-Williamson approximation ratio, also referred to as alpha GW. And so this approximation ratio is surprisingly enough believed to be optimal. And there are matching integrality gap constructions. A simple integrality gap construction, gives you, with a fairly simple construction, you can get an integrality gap of something like 0.88. So with that, I'll end the discussion here. So this is a fairly big topic that has been, and it's an important result, and it introduced semi-definite programming to the toolkit of theoretical computer science, which has then been very successful in solving a large number of problems.